Now we're going to shift our focus to the direction of vectors and finding the angles at which vectors go. And I want to back you up a little bit, go back to the unit circle for a minute. When we were looking at an angle who had an x and a y, and if we were on the unit circle, we found that the hypotenuse, we made that be 1, so that we had a unit circle, a radius of 1. And when we did that, we found that the x component, if our theta was right here, the x component was just the cosine of the angle, and that the vertical component, the y part, was just the sine of that angle. Again, because we have opposite over hypotenuse, and the hypotenuse is just 1, so the opposite is the sine. Same with the cosine, but with the adjacent. So we're dealing with vectors now, and instead of having a radius of 1, it's basically like we're taking our radius and extending it. So instead of talking about this as a vector, or as a radius, we're talking about it as a vector. So if I were to take this hypotenuse, which represents a vector, and double it instead, so that this is now 2. So this, now the length is 2. Well, that would also, of course, extend out my sides. I'd have to go a little bit further out this way, and I'd have to go further up. We're just dealing with similar triangles here. So if my hypotenuse doubles, that means that my vertical component also doubles, so this would be 2 times what I had for the side length before, which was just the sine. Likewise, my horizontal component is also going to get longer, and it's going to double, so I'm going to take 2 times what I had before. That is if my scale factor is 2. Notice that's also the magnitude of this blue vector. Its magnitude is 2. So that's the idea behind what you see here. We have the magnitude times the cosine for the horizontal component, and we have the magnitude of the vector times the sine of the angle for the vertical component. So it's just taking a unit vector and stretching it out. If we want to go the other direction, if u is the unit vector in the direction of v, then I believe you already have this on yours. I do not. But u, the unit vector, is the vector v divided by the magnitude, or that's how you find a unit vector, times the components that are the cosine of the angle and the sine of the angle. So it's just stretching it out. And actually this one's shrinking it back down, perhaps. Another really useful tool is the fact that the tangent, right here, is the sine over cosine. That should be pretty familiar to you by now. And if we're dealing with something that's not a unit vector, we're going to be multiplying it by the magnitude. These are just the components that you saw from up here. It's this component and this component. So it's this one over this one. And if we were in AI plus BJ form, well, this would simply, this part would be this, and this part would be this. So you can also just look at the fact that if I put these all together, that the tangent of theta is the b over the a, and then it's very, very easy to find out what angle and what direction that vector is headed. So let's practice that a bit. Alright, so here we have 2 vectors in a linear combination form. We're supposed to find the magnitude and the direction angle of each vector. Well, I might want to sketch this out first to give me an idea of where this is. Now these are both positive, so I'm pretty sure I'm going to be in quadrant 1. Keep that in mind. I'm in quadrant 1. I'm going to go 12 this way, and I'm going to go up 15. So there's my vector right there. Over 12 up 15. Magnitude of v Remember, it's just like Pythagorean theorem. You have 12 squared plus 15 squared, and we're going to take the square root and type that in. That's going to be the square root of 369. Now we can also break that down just a little bit, and I will trust that you can do that. Pause if you need to, but it's 3 times the square root of 41. All right, so there's the magnitude. Now, the direction. What is that angle? What is this angle right in here? Well, we used what we had on the slide before, that the tangent of theta is b over a. Now, our b is 15, and our a is 12. Look back at the triangle. It's your opposite over your adjacent. It's the tangent. So to find out what that theta is, we are going to do the inverse tangent. So theta equals the inverse tangent of 15 over 12. Make sure you're in degree mode, and when you calculate that, it should give you 51.3 degrees approximately. And that sounds good because we are in the first quadrant, so yes, that will be 51.3 degrees. So there's the magnitude and the direction angle for that vector. So it's going out a distance of square root of 369, and the angle that it's headed is 51.3 degrees. Now let's take a look at the second one. Notice that these guys are both negative. That means that we will be down in the third quadrant. So this way is 4, and then we're going to go down 7. So here's our vector. Just a different color. So here's our vector. It's going down. We are in quadrant 3. That will be important to us here in a moment. Well, let's find the magnitude. So the magnitude of the vector is the square root of -4 squared plus -7 squared. And that's the square root of 16 plus 49, which is 65. So this is the square root of 65. And that's 13 times 5, so it can't be reduced anymore. So there's our magnitude. Now we need to look at the direction. So we'll start out doing what we had done before, that the tangent of theta is b over a, so -7 over -4. So what we're going to do then is take the inverse tangent of, well, that would be 7/4 when it reduces. And it's going to tell us that the angle is 60.3 degrees. Now keep in mind we're in the third quadrant. So it's telling us that our angle is over here. This is 60.3 degrees. That's not where we want to be. In fact, it's 180 degrees from where we want to be. Therefore, we're going to take, to find our theta, take that 60.3 degrees, and we're going to add 180 degrees onto it, and we will arrive at 240.3 degrees.